All right, well, hello everyone, and welcome back. In this video, we are going to introduce sinusoidal signals and transition into AC circuits. All right, so here's our goals for today's video. First, we will briefly review our approach for solving second-order circuits using second-order differential equations. But as we've been discussing, it's kind of a pain to solve second-order differential equations. And we'd like to have an easier way to solve AC circuits and circuits with capacitors and inductors. So what we're going to learn about in this video is how we can represent sinusoidal signals as complex numbers. Specifically, we call these phasors. So we'll review important parameters for sinusoidal signals, and then we'll learn how to represent sinusoidal signals as phasors. And we will see that by representing signals as phasors, we can actually make our life a lot easier, and we won't have to solve those differential equations anymore. Finally, we'll practice converting voltage and current signals between sinusoidal and phasor forms. So let's first start by reviewing what we know so far. In our past videos, we learned about how to solve second-order circuits using differential equations. Let's try one last example of a second-order differential equation to solve a second-order circuit. Then we will move on to learn about how phasors can make solving these circuits significantly easier. So here we're told that we are designing an accelerometer which contains this RLC circuit shown. And we've been given the second-order differential equation, which describes this circuit for time t is greater than 0. And we're also given the values for the current source, inductor, capacitor, and resistor. So here we're asked to determine our inductor current IL of t, and let's find our inductor current IL of t for time t is greater than 0. We are also told we can assume the initial conditions, dIL dt is 5 at time 0, and our inductor current IL of t is 0 amperes at time t equals 0. So let's go ahead and use our 10-step recipe that we've learned in order to solve this problem. Since we were given the differential equation, we can go ahead and start at step 3 of our recipe. So let's go ahead and review what we are given. We are given our second-order differential equation is given by second derivative dIL dt, plus we have 1 over RC dIL of t dt, plus 1 over LC IL of t equals our current source IS U of t divided by LC. And remember here that U of t is our unit step function. So remember, at time t less than 0, U of t is equal to 0. But at time t is greater than 0, U of t is equal to 1. So let's go ahead and substitute what we know into our differential equation. So let's go ahead and substitute R, L, C, and IS to our differential equation. And if we do that, let's see what we get. We've got our second derivative term, plus we have 1 over RC, so that is, remember, make sure units are farads, ohms, and henries here. So in this case, our resistor R is 22.36 ohms times capacitance, which is 0.5 millifarads. Remember, that is, since there are 1,000 millifarads per regular farad, we get 0.005 here, or 0.005 farads times dIL of t dt. And then we have 1 over LC, so that will be 1 divided by our 1 Henry times our capacitance, which is, again, 0.0005 farads. And then that will equal our current source IS, which is 2 amperes times U of t divided by LC. So if we simplify, we will get the following equation. So our 1 over RC term will become 89.44 dIL of t dt. And then this 1 over LC term becomes 2,000. And then that will equal, on the left-hand side, or on the right-hand side, we have 4,000 U of t. And then, of course, for time t is greater than 0, that's going to be equal to 4,000. So this is our differential equation. This is the end of step 3. Remember that the most challenging part of these second-order circuit problems is finding that differential equation. Now, all that's left is to solve this differential equation using your favorite techniques. Here, let's go ahead and solve it using the recipe that we've learned. So in step 4 of our recipe, we need to determine our values of damping coefficient alpha and resonant frequency omega naught. So you'll remember in this case, this 89.44 term is 2 alpha, and this 2,000 term is omega naught squared. That comes from comparing our second-order differential equation to the general form. So in step 4 of our recipe, we find alpha and omega naught. So in this case, we determine that 2 alpha is 89.44. So that means our alpha value will be 44.72. Similarly, our resonant frequency omega naught squared is going to be equal to 2,000. So if we take the square root, we determine that our omega 0 is also 44.72. You'll remember that if alpha and omega naught are equal, we are critically damped. The next step of our recipe, step 5, is to find our roots, S1 and S2. We use these roots to help us determine our natural response. So here we know that S2 and S1 are given by these square root expressions. So let's go ahead and find S1 and S2. And here we determine S1 is negative alpha plus square root alpha squared minus omega naught squared. S2 is negative alpha minus r square root. So just plugging into those expressions. And of course, in this case, our alpha and omega naught are equal, so we end up determining that S1 and S2 are equal, and they're both equal to negative 44.72. Let's move on to our next step. In step 6, we need to look at S1 and S2 and determine our natural response. Here, since S1 and S2 are equal and real values, we are critically damped. And so we know that our natural response must be given by the expression shown in our recipe. So knowing that, we can complete step 6. So we know since S1 is equal to S2, which is equal to negative 44.72, we know that our natural response, I'll call it IL, N of t, we can take that from our recipe to be e to the negative 44.72t times k1t plus k2. So again, this is our critically damped case. And remember, of course, we'll leave these constants k1 and k2 as constants for now. But we will find k1 and k2 later when we use our initial conditions. Let's continue with step 7. In step 7, you'll remember that we need to guess the form of our forced response. And then we plug our guess back into our differential equation to determine the value of that forced response. So if we look back at our differential equation, notice that for time t is greater than 0, our forcing function f of t is 4,000 for time t is greater than 0. So since our forcing function f of t is equal to 4,000, we have a constant or a step source. And you'll remember from our prior videos, that means we need to guess that our forced response IL, f of t is equal to n, where n is some constant. And we need to substitute n back into our differential equation. So we go ahead and do that. And remember, we're just going to substitute n back into our equation that we're trying to solve. So here's what we get. we have our second derivative term, d squared dt squared of n, plus we have 89.44 dil dt, so that will be 89.44 times d dt of n. And then we have 2,000, so 2,000 times n. And then on the right-hand side, all of that must equal 4,000 because we're looking at time t is greater than 0. So remember that the derivative and second derivative of a constant is just 0. So those first two terms go away, and we are left with 2,000 n equals 4,000. We determine that the value of n must be equal to 2. So our forced response, IL, f of t, is just 2. We're almost finished. So remember, in step 8, we determine our complete response by summing our natural and forced response. And then we use our initial conditions in step 9 to determine any remaining constants in our natural response. So let's go ahead and complete those steps. So our complete response for IL of t, that is going to be equal to our natural response plus our forced response. So if we sum those two together, we determine that our complete response is e to the minus 44.72 t times k1t plus k2 plus our forced response, which was just 2. And in step 9, we need to determine our constants, k1 and k2. And we can do this using our initial conditions. In this case, remember our initial conditions were given to us. So we can use these two initial conditions to write two equations for k1 and k2. So our first condition is IL at time 0 is equal to 0. So if we substitute that in to our equation, we determine that 0 must equal e to the minus 44.72 times 0 multiplied by k1 times 0 plus k2 plus 2. If we simplify this thing, remember e to the 0 power is just 1. k1 times 0 is 0. So here we determine that 0 must equal k2 plus 2. This gives us that k2 must be negative 2. Our second initial condition is the derivative. So one thing to be careful of here, when taking derivatives, be careful to use the product rule. You'll notice in this case, when we take the derivative of the complete response, we have multiple terms that are functions of time that are multiplied together. So if we have, for example, the derivative of f of t times g of t, remember by product rule, we have to take the sum of the derivative of the first function times the second plus the derivative of the second function times the first function. So be careful here. Make sure that you remember to use product rule when taking this derivative. So let's go ahead and do our derivative for IL of t. And in this case, we know dIL at time 0 dt is going to be equal to 5. And that must equal, here we have e to the minus 44.72t. Let's call that our f of t. And then we have multiplied by k1t plus k2. And remember, derivative of 2 is just going to be 0. So if we take the derivative of IL of t, let's see what we get. Derivative of our first term, e to the minus 44.72t, that just becomes minus 44.72 e to the minus 44.72t. And remember, by product rule, the derivative must be the product of the first term's derivative times our second function. So here we'll multiply our derivative by k1 t plus k2. And then we take the derivative of our second function. That will just be k1. And then we multiply it by e to the minus 44.72t. Notice, of course, that we are looking at time t equals 0, so we plug in zeros for our time. And if we do that, this term becomes 1, this term becomes 0. We know k2 is going to be negative 2. This term becomes 1. So if we simplify that whole expression, we'll determine that 5 must equal negative 44.72 times our k2 value, which is negative 2, plus our k1 value, which we don't know yet. So if we solve for k1, we can determine k1 is just going to be equal to 5 plus 44.72 times negative 2. So k1 is equal to negative 84.44. So finally, we have found k1, we have found k2. We can now determine our complete response and our final answer. So here we substitute k1 and k2, and we get IL of t is equal to e to the minus 44.72t multiplied by our negative 84.44t plus our k2, which is minus 2 in this case. And then we have plus our forced response, which is just 2. And units, of course, here are amperes. So there you have it. Notice that if we follow this step-by-step recipe, we can still solve these second-order differential equations. So please make sure that you go back through and make sure you understand these steps. After you do a few examples of this recipe, it should be a lot more straightforward. Of course, we'd like to be able to solve circuits like this using an easier approach. And the good news is, starting with today's video, we're going to learn some new tools that will make solving these circuits a lot easier when we're dealing with AC sources. So let's go ahead and continue on with some good news. As you can see from our previous example, those first and second order circuits can get pretty mathy to solve. And you'll remember if we have a sinusoidal source, it can be even more effort to determine your complete solution and those constants. But starting with today's video, we're going to learn some new tools. And these will help make the math much easier. So we're going to learn how to use phasors and complex numbers. And we'll see in the next 2 to 3 videos that these tools make AC circuits significantly easier to solve. So just a reminder, let's review where we are heading. Over the past few videos, we've been adding more components to our DC circuits to make them more interesting. We've talked about how to solve circuits with capacitors and inductors. And now we want to start focusing more on AC circuits. But in order to do this, we need to add a few more tools to our toolbox. So in our next couple videos, we're going to review these new tools. And then we'll apply them to AC circuits. So we're first going to review sinusoidal waves. We'll review a little bit of math and trigonometry. Then we're going to learn about complex numbers and phasors, and how this helps us simplify things. And finally, we also want to make sure we remember to keep track of whether our calculator is in radian mode or degree mode. We're going to be doing a lot of sine and cosine calculations, so it's very important you remember which units you are working with. Let's go ahead and get started with these new tools. So first, let's begin with some key terms. We're now transitioning into the part of the class where we're talking about AC circuits. Basically, in our past videos, we've been focusing almost exclusively on DC circuits. So here's the differences between the two. DC stands for direct current. In a DC circuit, current flows in one direction only. Most of the time, current is also constant with respect to time. And in an AC circuit, AC stands for alternating current. In an AC circuit, current can actually reverse direction. So it might flow forward, then backward, then forward, then backward. And an official textbook definition of AC circuits is a steady-state circuit in which all of the inputs are sinusoidal and have the same frequency. So in order to really understand AC circuits, we need to make sure that we really understand how to deal with sinusoidal functions and sinusoidal inputs. So let's go ahead and review some key terms about sinusoids and waveforms and the different kinds of sinusoidal signals that we can see. First term here is a waveform. A waveform is a graph of current or voltage as a function of time. And often the waveforms we're looking at are periodic. A periodic waveform is a graph that repeats itself. So the waveform has some specific pattern, and it's just repeating cycle after cycle of the same function. A sinusoid is a wave which has a sine or a cosine shape. Notice that it could be shifted to the left or right. It doesn't have to be a perfect sine of x or cosine of x, but basically any wave that has some sine or cosine in its function. One other thing to note about AC circuits and AC waveforms in particular is that if we have negative values of voltage and current, that means that our polarity is actually opposite. And so current can actually flow in the opposite direction as when our voltage or current is positive. So we can see that for something like this, depending on whether our sinusoid is positive or negative, we could have current and voltage alternating directions. So another thing to be careful of here is degrees and radians. We're going to be using sine and cosine very frequently during the next few lectures and assignments. So you absolutely don't want to be making silly mistakes by using the wrong units. So please make sure you know whether you are in radian or degree mode when doing calculations. Here's a quick way to determine which mode you are in. If you are in radian mode, then cosine of 90 will return a negative number, which is cosine of 90 radians. But if you're in degree mode, cosine of 90 returns 0, because cosine of 90 degrees is 0. So if you ever need to do a quick sanity check, cosine of 90 is a good way to quickly check which mode you are in. All right, so we mentioned that waveforms are very important when dealing with different types of AC or sinusoidal inputs. And so the function generators that we use in circuits class and in electrical engineering, we commonly make waveforms of these different types. So first common type is sinusoidal. And function generators actually create all the other waveforms using a sinusoidal function as its input. So by using constructive interference between multiple sinusoids, it's actually possible to create square, triangle, and sawtooth waveforms. So depending on what kind of behavior you're trying to get in your circuit, you may need a square wave to have sudden on or off pulses, or a triangle to have sort of a ramped increase or decrease, or even a sawtooth. So these are some of the most common waveform types that we see in this course. When we talk sinusoids, we often refer to the general sinusoidal function shown here. We have, in this case, if we have some voltage signal or some function v of t, we often write sinusoids in the form a sine omega t plus theta. So let's just briefly review the key terms of this sinusoidal function. Some of these may be familiar to you from math class or physics class, but we're going to use this a lot, so please make sure you remember these terms. All right, first term is amplitude. So often we use letter A to be our amplitude. And please be very careful here to pay attention to how we define amplitude. In this case, we define our amplitude A as the height of our oscillations. So notice this is height relative to the center axis. And the units of amplitude are the same as our main function that we're looking at. So if it's a sinusoidal voltage function, our units will be volts. If it's current, our units will be amperes. But notice here, for the purposes of this course, when we say amplitude, we are referring to the height of one oscillation. Please be careful not to confuse amplitude with what's called peak-to-peak amplitude. Often on our electronics equipment, like on our function generators, we actually measure 2A, or peak-to-peak amplitude, when we are creating these sinusoids. When we say peak-to-peak amplitude, that is our height of our wave from the highest point to the lowest point. So that will give us 2A. And once again, often function generators will report peak-to-peak amplitude, or 2A, rather than plain old amplitude A. So whenever you're measuring amplitude, be careful and make sure that you pay attention to whether you are measuring the height of one oscillation or peak-to-peak amplitude. We see that often in lab we'll be measuring peak-to-peak amplitude because it's easier to get from the function generator or from our oscilloscope. But in our calculations, we generally use regular amplitude A. All right, our next important property is period. Period is often abbreviated by the symbol T. And period tells us the amount of time it takes for our sinusoid to produce one cycle. So units of period are seconds. It's basically time required for one cycle of our wave. Another very important property is frequency. Frequency tells us the number of wave cycles per second. And of course, frequency is calculated by taking 1 divided by t. And generally, we report frequency in units of hertz, where 1 hertz is 1 cycle per second. Often in the lab, we measure our frequency by looking at the amount of time it takes to go from one cycle of the wave to the next, and that will give us our period. All right, another really important term that we'll use is frequency in terms of angle. And so we call angular frequency our frequency written in radians per second. Angular frequency is given the symbol omega. So that's the Greek letter omega. So not W, but omega here. And to calculate angular frequency, remember there are 2 pi radians per 1 full cycle of a sinusoid. So we therefore calculate angular frequency using 2 pi times our frequency, or 2 pi divided by our period. So angular frequency tells us the size of the angle covered per unit time. So generally, this is radians per second. And one thing we'll notice is that generally we like to report angular frequency in units of radians per second. We'll see later that we actually report our phase angle in degrees, and we'll learn that this actually makes our calculations a bit easier later on. So it's very important that you pay attention to which units you're working with. Make sure you keep angular frequency in radians per second. One other thing about frequency is that it's helpful to just keep these relationships handy. If you ever need to convert between frequencies, make sure you remember period t is equal to 1 divided by frequency. And then also, if you want to convert between angular frequency and period, you can use those 2 pi equations. All right, one other important property we have here is phase angle. And that is the theta in our a sine omega t plus theta equation. Phase angle is really important because it tells us whether our sinusoidal wave has been shifted left or right from a reference point. We're going to see later that the phase angle can tell us a lot of very important information, and it comes up a lot. So the thing you want to remember about phase angle is that a full cycle is 2 pi radians, or 360 degrees. If we have a positive phase angle theta, our waveform will be shifted left. Basically, the waveform will happen sooner in time. So it's basically time advanced. We're advancing the wave so that it happens sooner in time. And a negative phase angle will shift our waveform to the right and delay that sinusoidal signal. And you can see that using our relationships between angular frequency and angle, we can determine how much time we are advanced or delayed using the expressions here. So another common situation that we come across in this course is very often we are looking at signals on an oscilloscope. So the oscilloscope shows our signal over time. And so for a sinusoidal wave, we often see a nice sinusoidal signal like the one here. This particular signal is some voltage signal. And often what we'll need to do if we're in the lab is we often need to take a sinusoidal signal and write an equation for that signal and get the signal, for example, v of t equals a sine omega t plus theta. So often we want to write this equation. Thankfully, to do that, if we have a plot or oscilloscope trace of our signal, it's pretty easy to find this equation. And so all we need to do is find each of the terms, a, omega, and theta. Here's the procedure that I recommend you follow if you need to find an equation for a signal. The easiest term to measure is our amplitude A. And on an oscilloscope, you can actually have the oscilloscope measure peak-to-peak amplitude for you using the measure button. And here we can directly see that our 2A is 1.46 volts. Or we could look at the height of the oscillation and determine our amplitude that way. So in this case, we know there are 200 millivolts per division. That means each box here is 200 millivolts. So that means we can estimate our height A, and we see that that's approximately approximately equal to maybe 700, 750 millivolts, which is about half of what we had measured using peak to peak. Once we found our amplitude, the next quantity we want to find is period. On an oscilloscope, often you can directly measure period using the measure button. But if you do not have that, you can simply look at how much time it takes to complete one cycle. And in this case, we're told that each division on this oscilloscope is 5 milliseconds. So we see that our period is indeed about 10 milliseconds total. Third step is we find our angular frequency. And to do that, we just take 2 pi divided by our period. The last step is to find phase angle. And the easiest way to find phase angle is to choose a point on your sinusoid where you know both the voltage or the amplitude of that signal at that given point and the time value. Then you can take that known point and plug it in to your equation. Since you also know A and omega, you can solve for theta. Then you can substitute in your theta value to get your final equation. One other thing to be careful of is sometimes we want to find our equation in the form A cosine omega t plus theta. And just be careful there that there is a trig identity. So if you want to find cosine, you need to subtract 90 degrees from your sine phase angle. And you can always sanity check, remembering a positive theta will shift us to the right. Negative theta shifts our wave to the left. Let's go ahead and try a quick example of this before we move on. So in this example, we're given an oscilloscope signal, and we are asked to estimate amplitude, angular frequency, phase angle, and our equation. So when we say estimate here, you want to just eyeball the values or approximate the values based on the given information. Let's go ahead and try this using the plot that we are given. So first thing to find is amplitude. If you'd like, pause the video and see if you can find these different properties. Remember, for amplitude, we're looking for the height of a single oscillation. And if we eyeball the approximate height of our oscillation, we can determine that our amplitude here is approximately 15 volts. Remember, we are looking for our height of a single oscillation, not 2A, or our peak-to-peak amplitude. Next is our angular frequency. Remember, to find angular frequency, we can use the equation omega equals 2 pi over period. So let's find period. In this case, we need to find the time required for just one cycle. I'm going to go ahead and take a look at our peaks that we see. So my period t is going to be the time required for one full cycle of my wave to complete. I'm going to estimate that my first peak happens around 0.005 seconds. I'm just looking at this time value. And if I look closely at my plot for that second peak, I'm going to estimate that this second peak for the full cycle of my wave occurs at about 0.037 seconds. Remember here, we're just estimating, so you eyeball the time as well as you can. In this case, we determine our period t will be the time it takes to complete that full cycle. So that will be 0.037 seconds minus 0.005 seconds, or that gives us 0.032 seconds. I'm going to make sure your units here are seconds. Finally, all that's left is to divide 2 pi by 0.032 seconds. And if we do that, we get approximately 196.35 radians per second. All right, the next value you want to find is our phase angle. And so in this case, let's find a known point on our graph. I like things to be 0 personally, so I'm going to go ahead and choose the time t equals 0 point. So I'm going to look at that point and I'm going to say that at t equals 0, I look at my plot and I'm going to say that my voltage V of t is equal to about 8 volts. You can substitute my point t V of t into our equation, V of t equals a sine omega t plus theta. So if I do that, here I have 8 volts, and that's going to equal amplitude of 15 volts times sine of 196.35 times time 0 plus theta. You can solve for theta. And I can determine in this case that 8 divided by 15 is equal to sine of 0 plus theta. So my theta is going to be inverse sine of 815, which gives me 32.23 degrees. Finally, our last step is to substitute into our equation. One thing to be careful of here is notice I used sine to find my theta, but here I'm actually asked to find cosine. It's more convenient to plug in and solve for theta using sine because sine is not an even function and you'll always get the correct theta value. But if I want to substitute my theta into a cosine function, I just have to be careful to use a trig identity. You'll remember from trigonometry that if I want to find sine of some value, that's the same as cosine of that value minus 90 degrees. So in this case, if I want to find my theta in the cosine term, I have to subtract 90 degrees from my phase angle I found earlier. So in this case, our theta will be equal to 32.23 degrees minus 90 degrees. So for the cosine function, our phase angle theta is actually going to be equal to negative 57.7 degrees. So just be careful there. Remember to use that trig identity if you need to change from sine to cosine. All right, so we have found our theta value, our omega value, and our a value. So we can finally determine V of t will be equal to 15 volts times cosine 196.35 t minus 57.7. And of course, our units here are volts. You'll notice once again that we often report theta in degrees units, but omega in radians per second units. And the reason for this is we'll see later that that makes it a lot easier for us to manipulate our phasors. So in this class, we often follow the convention to report our theta value in degrees and our omega value in radians per second. Again, we'll see why we do that a little bit later on. All right, so that's it for this example. So definitely make sure you're comfortable with this process. You may see a similar question as this on our next homework assignment. All right, so now let's return back to circuits. And why do we bother doing all this extra work with sinusoidal inputs? Well, we know that AC circuits have sinusoidal inputs, and AC circuits must also obey Kirchhoff's laws. The problem is, it's kind of a pain to add and subtract sinusoidal signals in that time-dependent form. What happens if our frequency is different? Or what happens if our phase or our amplitude is different? It can be a real pain to add or subtract sinusoidal signals. So we need a better way to deal with these. And the way we do this is by using phasors and complex numbers. So in the rest of today's video, we're going to review complex numbers and phasors. And we'll see that these really do help make our life quite a bit easier. So now it's time to add some of those complex number tools to our toolbox. Remember, when we talk about complex numbers, we're dealing with numbers that are based on the square root of -1. In math class, you probably called square root of -1 I. Mathematicians like to use I for square root of -1. But in circuits class and in electrical engineering, we don't want to confuse I with current. So you will see that in electrical engineering and in this course, we're going to be using J as the square root of -1. So please get in the habit for this course and for other electrical engineering courses you might take. Please use letter J to represent square root of -1. This is a very common convention that engineers use because we don't want to confuse complex number I with current. So first thing you might be wondering is, how can we write a sinusoidal signal as a complex number? That seems kind of strange. The reason we can do this is because of Euler's formula. You may have seen this formula before. It's a very important, very famous math formula. And mathematicians have figured out that e to the j theta, again here j is square root of -1, e to the j theta must equal cosine theta plus j sine theta. So if we have a sinusoidal signal of the form a cosine omega t plus theta, we can write that sinusoidal signal as a complex number a e to the j theta. And often, instead of having that e there, we get kind of lazy, and instead, many of us will write our complex number as we call it a angle theta, so a is some amplitude term, and then theta, of course, is our phase angle. So we can take a sinusoid, a cosine omega t plus theta, and we can rewrite it as a complex number. And again, remember, typically in this class, we do use angular frequency omega in radians per second, but typically this phase angle is reported in degrees. We say that a phasor is a sinusoidal signal represented by a complex number. So we can take any sinusoidal signal, a cosine omega t plus theta, and we can rewrite it as a phasor. We can also take a phasor in the form a angle theta and rewrite it back as a sinusoidal signal. And so essentially what we're doing here is we're taking a sinusoidal signal that is a function of time in time domain, and we are instead representing that signal as a function of frequency, or in frequency domain. And by converting between time domain and frequency domain, we can get out of solving those nasty differential equations and just solve a nice algebra problem instead. So we're going to see over the next few videos that rewriting sinusoidal signals as phasors makes it much easier for us to solve AC circuit problems. One other thing to watch out for here is notice our sinusoid must be in the form a cosine omega t plus theta. Notice if we have our sinusoid as a sine function, we have to first convert our sine to a cosine using that trig identity. Basically, you just have to reduce your phase angle theta by 90 degrees. Once you've converted sine to cosine, then you can convert your sinusoidal signal to a phasor. But be careful there. Sometimes this comes up on homework and exams. I might give you a sine function, and make sure you remember to convert that sine to cosine before writing it as a phasor. Let's try a few quick examples so that everyone gets the hang of this. In this example, we want to determine the phasors for these sinusoids, and let's write the final answer as a angle theta. So typically, when we want a phasor, we'll just go ahead and write the answer like this. If you'd like, pause the video and see if you can do this on your own. Otherwise, let's explain it together. The key thing to note here is that if we have a function in the form a cosine omega t plus theta, we can rewrite that function as a angle theta. So notice the amplitude A remains the same, and our phase angle theta also remains the same. So basically, just by looking at our sinusoidal function, we can directly convert that cosine into a phasor. So notice for I1 of t, it's actually a very quick conversion. If we want to convert that to function of frequency, we can basically say that I1 is going to be equal to our amplitude A, which is 120, and our phase angle is 60 degrees. So just like that, we just look at our amplitude, look at our phase angle, and we can find A angle theta. Pretty easy, right? How about I2 of t? Is I2 of t just going to be 100 angle negative 75 degrees? Careful. Notice I2 of t is equal to 100 sine 400t minus 75 degrees. We need to convert sine to cosine first. And remember, it's pretty easy to do that. We just have to use the trig identity. Basically, you just subtract 90 degrees from the phase angle. And so we determine that I2 of t as a cosine is going to be 100 cosine 400t minus 75 degrees minus 90 degrees, or 100 cosine 400t minus 165 degrees. So therefore, I2 in frequency domain, or in phasor domain, is just 100 angle negative 165. Notice units are still milliamps, but now we have I1 and I2 in frequency domain and written as phasors. So there's a few more things you should know about complex numbers. You may remember that we can write complex numbers in multiple forms. One way to write a complex number is in rectangular form, where we sum some real part A and imaginary part B. And we can determine that if we write our complex number as this sort of A plus JB, we can also plot this complex number on the complex plane, where our horizontal axis is the real part of our number, and the imaginary axis is the imaginary, or the J component of the complex number. So A plus JB would be A units to the left and plus B units vertical. I'm sorry, A units to the right of the 0 and B units vertical. You'll also remember complex numbers can be written using polar coordinates. And so we can write a complex number also in the form of a magnitude A at an angle theta. That's where we get this A angle theta notation that we commonly use. So most of the time, rather than writing A e to the j theta, we just write A angle theta. Notice theta is measured from the positive real axis and counterclockwise. So if we have a positive value of theta, then we measure it in that direction. So we can also write complex number as A angle theta. And we know by trigonometry, we can still relate that back to rectangular form. So for this class, it's very important that you know how to convert between rectangular and polar complex numbers. And thankfully, it's very easy to do so using trigonometry. So if we just draw a triangle, we recognize that we have a triangle with hypotenuse A and side lengths A and B. So we can easily convert between polar and rectangular forms using these equations. Please make sure you add these to your toolbox so that you know how to do these conversions. We'll do an example of this in just a moment. One other very important thing is that I certainly expect you to know how to use our equations to convert between rectangular and polar forms. So definitely know the equations on this previous slide. But I also understand that, it's tedious to do that calculation over and over. So on homework, you may use online phasor calculators to do the conversion for you. Again, the caveat is, unless I specifically tell you you must perform the conversion by hand, I will allow you to use an online calculator to help. In this website, you can find an example of a phasor calculator. And on this one, you can just go ahead and select convert in either direction, and it'll bring up this nice window. You enter the values that you have and then click convert, and you'll get the result. So here, the real number 3 plus J4 is converted to 5 angle 53.13 degrees. And similarly, you can convert from polar to rectangular by choosing the other option. So definitely check out this website, and you'll have an opportunity to practice these on the next homework. There's a couple more points I would like to bring up before we do our example. First is some naming conventions. You'll notice that we generally use lowercase I and V to indicate sinusoidal currents and voltages, but we use uppercase bold I and V to indicate a phasor in frequency domain. In general, remember phasors are functions of that input frequency omega. So often we write phasors as a function of frequency. But given that most of our AC circuits have constant frequency, we generally can get away with just writing our voltage and current phasors as capital V and capital I. You'll see that a lot of electronics books follow this similar convention. Finally, remember if we have a phasor A angle theta, typically we call A the magnitude, and theta is our phase angle. Lastly, I mentioned these terms about time domain and frequency domain. Remember, up till this point in the class, we've been writing sinusoidal functions as functions of time. So if you have a sine or cosine with a t term, that is a time domain function. It's a function of time for that signal. If we take this signal and write it as a phasor, notice now we have a angle theta, we have complex number here. We call this phasor domain or frequency domain because the signal is now a function of frequency or function of omega. Remember, in this case, our omega is 200 for that sinusoid. Let's go ahead and try a couple examples of this. So in example 3, we want to convert our phasor V1 to rectangular form and phasor V2 to polar form. First, we do it by hand calculations, and then we need to check our work using an online phasor calculator, such as the one at that website. Let's go ahead and give this a try. Let's start with V1. So for V1, we have an A and a theta value. So 4.25 angle 115 degrees, that gives us A is 4.25, theta is 115 degrees. And we know from our equations, we can determine that if we want this in rectangular form, A plus JB, we determine A using A cosine theta, and B using A sine theta. So all we need to do is substitute. We know A is 4.25, theta is 115. So we determine A is equal to 4.25 cosine 115 degrees. B is equal to 4.25 sine 115 degrees. Make sure you're in degree mode, and you'll see if your calculator is in degree mode, we get negative 1.796 for A, and we get 3.852 for B. That gives us V1 is equal to negative 1.796 plus J 3.852 in rectangular form. Let's now try V2. So V2, we know that V2 is negative 4 plus J3. So in this case, negative 4 is our A term, and B is 3. So from our equations, we can determine that we want to find A angle theta. We need to find A theta. From our toolbox, we know A is equal to square root of A squared plus B squared. So that will be square root of negative 4 squared plus 3 squared, square root of 25, which is just 5. And then theta depended on whether A was greater than 0 or less than 0. So in this case, we need to take the second version of this equation, and we determine here that our theta is going to be 180 degrees minus inverse tangent of 3 divided by negative 4. That gives us 143 degrees. So therefore, our V2 as a phasor in polar form will be 5 angle 143 degrees. So now let's go ahead and check our work using our phasor calculator. All right, so if we pull up our phasor calculator, let's first go ahead and check our phasor V1. So V1, we want to convert from polar form to rectangular form. So all I need to do is type in. My magnitude was 4.25. My angle was 115 degrees. I click convert. You'll see we end up with the same answer as we had calculated by hand. Our real part A was minus 1.796. Imaginary part B was 3.85. Then we can go ahead and check our second term, V2. V2 we want to convert from rectangular to polar. And in this case, I know my real part, A, was equal to -4. My imaginary part, B, was equal to 3. I click convert. I see my magnitude is 5. My angle is 143 degrees. So make sure you know how to do these calculations both by hand and using the phasor calculator. Most of the time, it's perfectly acceptable to use the phasor calculator, like in homework assignments. But if I specifically ask you in the instructions to do the calculation by hand, please make sure that you do the calculation by hand. So where do we go from here? So in this video, we've learned how to write our sinusoids and sinusoidal signals as complex numbers. And so in our next video, we're going to learn how to do math with complex numbers. And we'll see that we can use these tools to apply Kirchhoff's laws and more easily analyze AC circuits. We will see that these tools and complex numbers allow us to solve AC circuits without needing to do differential equations. And so, just as a spoiler alert, we're going to see over the next few lectures that when solving AC circuits, we can still use Kirchhoff's laws and our favorite DC tools. The only difference is that first we have to rewrite our circuits and all our circuit components as phasors and something we call impedances. Once we do that, we can solve our circuits as usual and use our favorite DC tools. So definitely take the time to make sure that you learn and understand these phasors and complex numbers. We're going to be using these tools frequently for the rest of the course. And you'll see that by using phasors and complex numbers, AC circuits become much easier to solve. Let's go ahead and wrap up for today. So you should now be able to solve second-order circuits using those second-order differential equations, but you should also see that there's light at the end of the tunnel, and there's an easier way to solve AC circuits using complex numbers and phasors. Make sure you understand those key terms we covered about sinusoidal signals, amplitude, phase angle, all that good stuff. Also, make sure you get comfortable representing sinusoidal signals as phasors and converting between sinusoidal and phasor form. We're going to be using these new tools pretty much for the rest of the course, so it's definitely important that you understand them. And in our next video, we're going to learn more about how these tools can be used to solve AC circuits and make our lives easier. Thanks, everyone, and we'll see you in the next video.